5.6, and 5.6 is on what is called linearization. It is called linearization. Linearization. And another way to phrase linearization is also called linear approximation. It's the same thing. Linear approximation is the same thing as linearization. Now let's consider an equation. If I have something like y equals 1 over x minus 1. What function family does this belong to? Is this linear, exponential, quadratic, cubic? What kind of function family does this belong to? Starts with an R. A. T. I. It's a rational. This is a rational equation. And I know it's a rational equation because it's written like a fraction. In fact, the definition of a rational equation or a function is a polynomial divided by a polynomial. The parent function for all rational functions, the parent function is y equals 1 over x, which would look something like this. Oops, let me draw that last one. So one of the characteristics of rational functions is asymptotes. And I don't know if it's obvious to you, but we have a horizontal asymptote here. We also have a vertical asymptote that the graph converges on as it goes further to the left and right, as well as going up and down. Now, looking at this equation right here, what kind of transformation occurred compared to the parent function? What kind of transformation occurred compared to the parent function? It's a horizontal shift. In what direction? It goes to the right. Yeah, we could imagine that we have parentheses here. And so whenever we have parentheses, it does the opposite of what we would expect. If you wanted to think of, where does this vertical asymptote, where does it shift? Well, the vertical asymptote is what is the x value that will give you 0 in the denominator, and it's a positive 1. So this is going to be a horizontal shift to the right by 1 unit. So we're going to, now the vertical asymptote is going to be a shift over by 1, and our graph is going to look something like this. Now, what I want to do is I want to find the equation for the tangent line when x is -1. So right now, the directions are, for this graph right here, I want to find the tangent line, find the equation for the tangent line at x equals -1. How do I do that? Eleanor, any ideas of how we would do that? So there's what is a tangent line? Yeah, it goes through 1 point on a curve. A more technical definition would be it goes through 2 points that are infinitely close to each other. That's going to rule out the possibility of this being a tangent line if I have something like that. So we're trying to go through something that just barely, we're trying to find the slope. A tangent line would be the instantaneous rate of change on any at any point for x. And so we would have, let's use, I don't know, blue. So we're looking for x equals -1. So let's say that this is -1 right here. And so our tangent line would be more or less a line. I don't know if this is going to be I don't know whether this is going to, something maybe like this. I don't know, maybe like that. So I want to actually find the equation of that tangent line that just barely, just basically calculates the instantaneous rate of change when x is -1. Well, what kind of function family does this belong to, this tangent line? It's linear, yeah. And because it's linear, wouldn't it be logical then that we should use y equals mx plus b? Okay. How would I find m? Yep, it is the slope, so I should find the derivative. So I'm going to find the derivative. So we need to find the derivative of this to find the slope. So my slope is going to be the derivative of y, which is what? How do I calculate the derivative of that? I think the quotient rule would be fine. I think the quotient rule would be completely fine. So what is the quotient rule? Yeah, low d high. What's the derivative of 1? 0. So low d high minus high d low. What's the derivative of the low? 1 over low. X minus 1. X minus 1 squared. Okay. And so that's going to give, what does this part here become? 0. Yeah, that's 0. So I have 0 minus, what is this part here? What does that become? Okay, so I have -1 over x minus 1 squared. But I want to know the slope when x is -1. Okay, plug in the -1 for x. What do we get? Sorry, louder. -1/4. I'm going to plug that into here. That's going to give me -1/4. Is everybody good with that? That m is -1/4. Is everybody good with that? Okay, so I know what m is. How do I find b? I know what m is. How do I find b? A little louder. Plug in an x and y. Okay, so I have an x. I have an x right here. Well, where's my y? Yeah, let's plug it into the original equation to find our corresponding y value. So, oh, I want that part here. So so we have y equals 1 over -1 minus 1, which is what? Is that -1/2? Okay, so we have we call this the point of tangency. The point of tangency is that point where we have that tangent line. And that point of tangency is going to be -1, -1/2. So somebody said that let's just plug in, if we want to solve for this equation, for the equation of a tangent line, we should plug in our x, y, and our m value. So that's going to give me, let's just change colors. Let's do blue. That's going to give me, so I have this y equals mx plus b. Y we just calculated to be -1/2. So I'll say that -1/2 here equals m, which is -1/4. That's what we calculated here. And x was what they gave us in the problem, which is -1 plus b. Now what? How do we solve for b? That gives us -1/2 equals what? One-fourth plus b, okay. Now what? All right, if I take it away, that gives me -1/2 minus 1/4 equals b, right? How do we subtract fractions? Common denominator. So what am I going to multiply to this to get a common denominator? All right, so we're going to multiply by 2/2. So we're multiplying by 1. We're really multiplying by 1, so none of the quantities change. So that gives me -2/4 minus 1/4 equals b. So what does b equal? Louder? -3/4. So my equation then is y equals what? What was the m value? Yeah, -1/4. So I have -1/4 x and then -3/4. So that's our equation. So I'm going to, let's just zoom out a little bit so we can see it all. So I'm going to go to Desmos and just, I think it's always satisfying after you find something like the equation for the derivative, for the tangent line. And it's sort of satisfying, in my opinion, to graph it and see that we did indeed have the right answer. So I'm going to type in our original equation of y equals 1/x minus 1. So that's what we said, that it would shift to the right, and it looks like it did. And then our equation for the tangent line was y equals -1/4 x minus 3/4. How did we do? Yeah, it looks like we did pretty good. Yep, that's the point of tangency when x was -1. That's what was told to us up here. And it looks like, yeah, it just grazes the top of the curve. Okay, now we've done this before, right? This isn't the first time we've done a problem like this. But now I want to talk about this new idea of what is called linearization, or it can also be called linear approximation. Now, what I'm going to do is I'm going to use this equation to calculate values for, in this case, I'm going to use the blue equation to calculate values for the red equation. Now, that only works for values that are close to this point of tangency. Why would an approximation for the red graph only be effective using the blue graph for values around the point of tangency? Why would it only be effective to use the blue graph as an approximation of some value for the red graph close to the point of tangency? Why would it only be effective to use the blue graph to approximate y values for the red graph for points around that are close to the point of tangency? It's not very accurate. You can see that at first around here, around that point, it looks like they're really close. The values would be good approximations. But as you go further away, you can see that these lines diverge. They get further and further away from each other. And so, yeah, if I were to try to calculate, if I wanted to use the blue graph to approximate a y value for the red graph when x is -4, that probably wouldn't be very accurate because you can see that the two equations that they diverge from each other. So let's go back here. So the idea, what is the idea? And what does linearization mean, or linear approximation? It means we're approximating using what? A linear equation, yeah, a linear equation or a linear function, yeah. So let's spell this out. The idea of linearization. Is using the tangent, the equation for the tangent line is to use the equation for a tangent line to approximate y values on our curved function, on our original function, on our original function. Emerson, how are you doing? How are you doing?
Good.
What is linearization?
You use like a tangent line and you measure the tangent line so you can figure out like y values on like the equation.
Yep, correct. Nice. So we're going to use our tangent line, our equation for the tangent line, to make an approximation of our y value from the curve, the original curve. Okay, so let's do an example. So I want to approximate for the previous problem, from the previous problem, from, or I'll just say for y equals 1 over x minus 1. That was our previous equation that we graphed, and then we found the derivative, and we even found the equation for the tangent line, which was here. So for y equals 1 over x minus 1, use the equation for the tangent line to approximate x equals -1.1. Will this give me an acceptable approximation? Is -1.1, is it close to our point of tangency? Yeah, so this would be a good approximation. So our tangent line is right here. So what do we get? What do we get? Y equals -1/4 times -1.1 minus 3/4. What do we get? Anybody have a calculator? Nobody has it? Miguel, did you get it? Eleanor, do you have it? No, that's fine. What's the rule for decimals in AP calculus for the AP test? Yeah, we just need 3 decimals. We just need 3, the 3 numbers after the decimal. That looks accurate to me. So let's go back to our equation, our graph, I mean. Let's zoom in and look at 1.1. Let's see if I can look at 1.1 and compare those. So that would be this point here. That's what we calculated. We said a good approximation when x is negative 1.1, then the y value is negative 0.45. Is that what we calculated? 475. Okay. Just, yeah, I might have just read it wrong. And then how does that compare with this one? So is that a close approximation? Yeah, I think that was pretty accurate. I think that was, if we do this one, I don't know if I have to do that. Yeah, I think that's pretty close. That one versus, oops, this one here. Oops. Yeah, I think it's pretty close, a pretty close approximation. Miguel, what's the point of linearization, or what is linearization?
Essentially just making the tangent lines in front of the y value.
Yeah, we're using the equation for the tangent line to make an approximation of our curve. Yeah. Okay, so let's do another one. Here's our next example. I want to use linearization to approximate the value of f of 1.2 if d dx of f of x equals negative x over y, and f of x passes through 2, 1. What do we do? ¿Qué hicimos? Catherine, what is linearization? Yeah, so we're going to use the tangent line, the equation to the tangent line to make this approximation. We want to make an approximation of this. Oops, wrong tool. We want to use the tangent line to make an approximation of this. So we need to come up with a tangent line. Emerson, any ideas?
You probably have to plug in 1.2 to the derivative.
Aren't we using this 1.2? Don't we want to find the approximation of this using the equation of the tangent line? So isn't the first step when we do anything with linearization, don't we have to find the tangent line or the equation to the tangent line first?
Yes.
How do I find the equation of the tangent line? It's a tangent line, which means it's linear. So Emerson, what comes to mind if it's linear?
Well, I guess B is a Y.
Okay. So how do I find my M and my B value?
Where I thought you would plug in.
So the derivative is going to give me, so what would that tell me? So Emerson says, let's take x equals 1.2 because that's what this is, right? When we do f of x in parentheses, that x has been replaced with a 1.2, meaning that's the x. If I plug that, what does the derivative calculate?
The slope.
The slope. So doesn't this tell me the slope at 1.2? Is linearization finding the slope? Is linearization finding the slope? The idea of linearization is using the equation of a tangent line to approximate the y value. I don't see anything here about slope, Emerson.
I thought you had to find the slope of the tangent.
All right, so yeah, so we have to find the slope of our tangent line. Now this isn't, so what, is this the point of tangency? Or is this the point of tangency?
Yes, 2, 1.
Okay. So I want to find the tangent line at 2, 1. Okay, yeah, I think that's a good idea. We'll plug that in. So our M, this means derivative, right? Okay, that just means the derivative. Just another fancy way of writing derivative. So I'm going to plug that in. So I have -1/2. Does that look right to you? Okay, so that's my slope. Now what?
Sorry, isn't it actually negative 2/1?
Is it 2/1? Oh, I did it backward. I apologize. Negative, that's my X and that's my Y. Yeah, I apologize. My fault. 2/1. So -2/1 or just -2, right? Okay, that's my M value. How do I find my B value? You plug in what? Plug in this X value? Don't I plug in both? Okay, so that would give me, so I have 1 equals M, which is -2. That's what we calculated M to be, times X, which is this value here of X of 2. And then plus B. Now what?
1.2.
So we're going to worry about the 1.2 last, right? Because the idea of linearization is that we want to use the equation of a tangent line to make our approximation of the curve. So I don't know what my function is, the original function, but I do know that I want to find an approximation of this 1.2. So I'll do that last. So right now I need to solve for B. How do I solve for B? What is B?
Well, we did it by itself, so -2 times 2 equals -4. Then we add +4 on each side. We get 5.
Yeah, B, yeah, I agree with you. B equals 5. B equals 5. So our equation then, our tangent line is y equals -2x plus 5. Plus 5. Yep, there you go. Is that what I wanted to find? Is that the answer?
No.
What am I trying to find? I'm trying to find my approximation of f of 1.2. So how do I do that? Yeah, now we can plug that into this equation here. So that gives me y equals -2 times 1.2 plus, let's move over a little bit, plus 5. What does that give me? Who has a calculator?
-2.4 plus 5.
So this part here becomes -2.4 and then plus 5. Yeah, positive 2.6, 2.6. Yep, there you go. That's the answer. That's my linear approximation. For
Accurate can this be for most studies?
as long as you're really close to that point of tangency, then it's more, we can say that it's fairly close. But the further you get away, we don't know. We don't know what the curves look like. And so the further you go, you move away, depending on how sharp that curve is, the approximation could be extremely different, completely different.
Regarding that, what is this used for?
What is this used for?
Uh-huh.
I think that if you like here, I never had the equation, right? Since I never had f of x, then I'm sort of stuck using the tangent line as my approximation. Here's the problem, Riley. Most of my training, I'm a 48-year-old man. Most of my training is in pedagogy and the science of education. I've been a special educator for 17 years, and then I became a math teacher for the last 11 years. And so a lot of the things that we use that I teach, that I don't have, you're going to have a better idea of where it's useful in the real world when you go out into the real world. And so there's a lot of applications for, say, quadratics. I know that quadratics, as far as falling objects, is great in physics, useful in physics, and useful for stopping distance versus speed. But there's a lot of other uses for quadratics that I might not even know about. So I don't. I don't have, this is part of the AP curriculum, and so I have to teach it. There is an application for it. I'm just not really sure what it is. When it comes to imaginary numbers, for example, the first year I taught imaginary numbers, I didn't know of any application for it. But then the further, the more I taught it, and the more students were frustrated of, when am I ever going to use this? Then I did some research, and I found that, you can't explain string theory and quantum physics and multiverses. You cannot explain those theories without those imaginary numbers. In fact, waves in general, even sound waves, there's aspects of sound waves that cannot be explained without imaginary numbers. So I would imagine that the more I teach this, and the more questions students ask me like this, the more I'm going to do my own research and find where it's valuable. But right now, I don't have a good answer for you. All right, so the next question uses trigonometry. And from yesterday, I can imagine that some of you are going to be a little rusty on this, which is fine. It's just a way of reminding ourselves of some important things when it comes to trigonometry. In fact, when it comes to trigonometry, consider our unit circle. And a unit circle, by definition, is a circle that's centered where? A unit circle is centered where? At the origin, at 0, 0. And it has a radius of what? It has a radius of 1. If it has a radius of 1, what does this point right here have to be? It has, well, all points have an x and a y value assigned to it. All of your in two-dimensional space. It has an x and a y value assigned to it. What is this point right here? It's 1, 0. Okay, 1, 0, 1 over, and no spaces up or down. So that would be 1, 0. What's this point right here? What is it? That would be 0, 1. What's this point here? Negative 1, 0. What's this point right here? 0, negative 1. And let's consider that if we have, here's our unit circle again, and I have some point on the unit circle. This is my x value and this is my y value. And that means that to get to this point, there was a certain amount that I had to go over. Let's say that would be x, and a certain amount that I had to go up. We'll call that y, with a radius. With the radius of what? What was the radius for a unit circle? It's 1. So we could construct a right triangle here with some value of theta. In fact, for all conceptual understandings of trigonometry, we always start at the initial x-axis, and then for positive angles, we rotate around counterclockwise. For negative angles, we rotate the other way. Now, for what would sine of theta be based upon this triangle here? Yeah, y over 1, and y over 1 is what? It's just y. And cosine by definition is adjacent over hypotenuse, and adjacent over hypotenuse is what? It's x over 1, and x over 1 is x over 1. So we know that sine is our y value and cosine is our x value. That's pretty important when it comes to understanding trigonometry. And then let's consider our radians. In this class, it's exclusively radians. We're not using degrees in AP Calculus. And so in radians, we start at the initial side here. If it's counterclockwise, it's a positive rotation. What is that in radians? A half circle rotation in radians? It's pi, yeah, it's pi. And then if I have something, what if I had a quarter rotation? That has to be pi halves, yeah. That has to be pi halves. So I think that's everything that we really need to know in order to understand how to do this problem. So I can scroll down a little bit and we'll do this problem. So this problem says I want to find the linearization of f of x equals cosine of x at x equals pi halves. I want to use it to estimate f of 9 pi 16ths. I don't know if you can you see that it's 9? What do I do? What do? If it's linearization, what comes to mind as the first step? Yeah, find the linear function. Specifically, we're talking about the equation of the tangent line, right? We need to find the equation of the tangent line, which means we're dealing with this y equals mx plus b. How do we find these m and b values? Okay, let's take the derivative of f of x. That will give us our m value. So we have the derivative of f of x equals what? Do you guys remember what the derivative of cosine is?
Negative sine.
Nice. It's negative sine of x. If you are not using your flashcards, I would love if we could spend more time doing flashcards in class. We haven't been, so please keep up on those flashcards. All right, so I want to specifically know the slope when x equals what? Pi halves. So I'm going to plug that in. So so my slope then is negative sine of pi halves, which is what? Does anybody know? We just reviewed it. What is it? It is negative. Yep. So this part here is 1, right? And so then we have the negative 1. Yep. So we'll just move up, and so this rotation right here of pi halves puts us right here, and our y value at that point is 1. And so that gives us negative 1 because of this negative here. All right. So I need to find a b value. Now what? Yep. Well, I have to find a y value too, right? If I know m and I know x, if I can find y, I can solve for b.
So cosine of pi halves.
Yeah, let's just plug this into the original, and that will tell us our corresponding y value. So let's plug that in to find y. Plug x equals pi halves into original. So that gives me f of x, which is really my y value. Y equals cosine of pi halves, which is it's 0. Let's go back and refresh ourselves. I go back up to the top. If I rotate by pi halves, then I get cosine is my x value. The cosine will be 0. Cosine of pi halves is 0. Okay, so now what? Y equals, actually we need to plug these values in. Yeah, y equals 0. So y equals 0. So we're trying to solve for b, right? 0 equals m. What was m? Negative 1. X pi halves plus b. So b equals what? So b equals what? Kata, what does b equal? Yeah, just pi halves. This gives us negative pi halves, and then we add pi halves to both sides. Pi halves plus 0 is just 0, and so I just get b equals pi halves. Yep. So what's our tangent line? Tangent line is y equals negative 1x plus pi halves. Okay. But what was the goal? What are we trying to do? Riley, what's that?
So we want to find where f of x is 9, or sorry, we're trying to plug in our x value of 9 pi over 16.
Yeah, let's plug that in for our x value, and then we can approximate what that y value is. So that would be 9 pi 16ths. So I have y equals negative 9 pi 16ths plus pi halves. Now what? What do we do when we add and subtract fractions? Yeah, so we're going to multiply. If we need a common denominator, we need to multiply this by something so that we get the same denominator. We're going to multiply by 1 because we don't want to change the quantity.
8 over 8.
Yeah, we're going to multiply by 8 over 8.
Yeah, those together we'll get 17 pi. Oh, actually. Just get pi 16.
Plus or minus? Is it positive or negative?
Negative.
Yeah, I get negative pi 16ths. There you go. That's the answer. Next one. Kyla, how are you doing? Cool. Kyla, what's linearization? Yeah, for the curve, or for whatever the original equation was. Yeah, I agree with you. All right, so let's go ahead and do another one. So I have if f prime of x comma y equals negative 4x minus 2y over x plus 2y, and f of negative 1 equals 2. Use linear approximation to estimate f of negative 0.9. Emma, where do I start?
equation now, or do you start from, I'm not exactly sure.
What does this mean right here? Oops, wrong tool. What does this mean right here?
That's the derivative,
And the derivative means what?
the inverse,
The inverse? Is this
or
the same thing as this? No, they're not. What does the derivative give us?
The rate of change.
It gives us the rate of change. It gives us our slope. So this is it's already the slope equation. It says f prime of x comma y. It's just another fancy way of saying this is the derivative. This is the derivative. So if if I have to use linear approximation or linearization, it's the same. Well, Emma, what is linearization?
linearization is using like the tangent lines to approximate values.
So I need to come up with a tangent line. And it's a tangent line. So what equation comes to mind when you think of a tangent line?
The y equals x plus b.
Nice. Okay. So how can I find my m and my b value? Emma, what does your derivative give you?
The m.
It gives you your m, right? It gives you your slope. Is there a way I can find my slope? My slope when x equals what?
When x equals -1, y is
Right, that's my x value. So, oh, let's just plug in our x values here, and my y value here and here. Does that work? Yeah. So my m value is -4 times x, which is -1, minus 2 times y, which is 2, over x, which is my -1, plus 2 times y, which is 2. Emma, are you okay with that? Okay, what's the answer to that?
Does not have zeros in the numerator, so it doesn't exist.
It does exist, but what is it?
Just 0.
Yeah, I have a zero slope. What does it mean to have a zero slope? What does a zero slope look like? Yeah, it's just a horizontal line. So I have some horizontal line where this is 0, so it doesn't exist. I just have a b value. How do I find a b value?
Well, it's just the lines.
Okay, what's the y-intercept?
When x equals 0.
All right, so let's plug in values. What is y? Yeah, it's 2, because of right here, 2. And then what did we calculate m was? 0. So equals 0 times x. What's x? Yeah, it's -1. I agree with you. It's -1. And then plus b.
Oh, and then you can just solve that.
So what is b?
Just 2.
Yep. So if I plug that into my equation, I have y equals 0x plus 2. This can be simplified to what?
So just y equals 2.
Yeah, it just becomes y equals 2. It just becomes y equals 2. So I have y equals 2. Now I want to estimate when x is what?
0.9.
What is y when x is -0.9 for this equation?
So
It's, yeah, in fact, y is always 2. Y is always 2. 1, 2, y is always 2. When x is 0, y is 2. When x is 1, y is 2. When x is 2, y is 2. When x is 3, y is 2. When x is 4, y is 2. X is y is always going to be 2. So the answer is then is -0. Oh, sorry. The answer is 2. The answer is 2. In fact, I'll write it this way. Maybe this is more helpful. If I write f of -0.9 equals 2.
I see the problem before this a little because I feel like I missed something.
This one up here
Yeah,
on trigonometry.
yeah.
Okay, so what we did, we had to find y equals mx plus b. We found m by taking the derivative of this, Miguel, right? So that gave us this. This is the derivative. We plugged x, which is this, into it to find our slope of -1. Are you good with that? Okay, now that we know what -1, we know m is -1, how do we find b?
We just plug in everything we have. To
How did we find y?
why we-
Don't we have to plug this into the original?
yeah.
That will tell us what our y is. Okay. And so that gave us our x and our y value, which is, where was that? I don't know where I wrote it. Okay, well, our x value is pi halves and our y value is 0. Yep. And then we plug in everything we know to solve for b. 0, -1, pi halves. Solve for b, we got pi halves. So I plug all that back in to get my equation of y equals -x, which is my -1x, plus pi halves. And then I still had to solve for this, right? So I plugged that, pi halves 6. I had to plug that in for x here and solve for y, which was this.
Yeah, I found out what I did. It's just I made a mistake and didn't write 9 times pi over 16. I just
Oh.
wrote pi over 16.
Oh, yeah. Okay, yeah, it's all good. All right, moving on. This whole entire day is about what? Linearization. Who have I not picked on? How about Ellie? Ellie, what is linearization? Perfect. Finding the tangent line, the equation for the tangent line to approximate the y values for the original equation. Yep, correct. All right, let's do another one. This is an AP problem. Maybe it's not so exciting to do an AP problem because all of your pre-tests, all of your tests, all of your retakes, they are all made up of past AP problems. But this is another AP problem right now from a past exam. Now this is, so I want to let f be a differentiable function. Such that f of 3 equals 2 and f prime of 3 equals 5. If the tangent line to the graph of f is used to find an approximation to a 0 of f, that approximation is 0.4, 0.5, 2.6, 3.4, 5.5. Wordy, 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 wordy. It's so wordy here, it might make you feel a little intimidated. It's not really that difficult of a question. It's more about understanding the verbiage. Does it feel a little intimidating that it's so wordy, wordy? A little bit? Yeah, I agree. I think it does because it's wordy, but if you look at it, if we understand it, it's really not that difficult. Now, I'd say probably some of the vocabulary that we should understand is this piece right here. Approximate, so it says find an approximation to a zero. Now, when I talk about a zero, Sam, I'm not talking about your ex-boyfriend, although he is a zero too. But I'm just teasing you anyway. I don't know who your ex-boyfriend is. What does this mean, a zero? It means the same thing as a root. What is a root? Does anybody remember this from last year in secondary math 3? What's that? Where y is 0. If it's a real number, it's also an x-intercept. If it's a real number, it's also an x-intercept. A 0 is an x-intercept if it's a real number. If it's not, then it's, well, it's, you still make y 0. It's the value of x when y is 0. A 0 is the value of x when y is 0. Okay. So it does talk about, it says, so find f, so let f be a differentiable function such that f of 3 equals 2 and f prime of 3 equals 5. If the tangent line to the graph of f is used to find an approximation to a 0 of f, what that approximation is what? I would say that if for your AP test, if you talk about approximations, this is something that might come to mind. Or we haven't talked about there's some other methods too where an approximation might come to mind. Any guesses where we should go from here? If the tangent line to the graph of f is used to find an approximation, that right here should tell us that what we're talking about is linear approximation. That piece. If the tangent line to the graph of x is used to find an approximation to 0, okay, that should tell you it's linear approximation.
So we're already at the f of f of 3 equals 5. So wouldn't that be already our m value?
What's our m value?
Yeah.
What is m?
Is it not 5? Or are we not?
It is 5. Yeah, it's 5 when x is what?
When x is 3.
Okay. Do we have enough information to figure out a tangent line?
Yes.
Okay. What is the tangent line?
Tangent line is f of x minus 13.
So we're using this y equals mx plus b.
5x minus 13.
So it's going to be 5x minus, where did you get 13?
I got 13 because I plugged in our y value, which is 2.
And your x?
And x, yeah.
Do you mind if we do that part as well? Let's just Sounds like you're ahead of us, so that's fine. So we're going to plug in these values. Where did you find that y is 2?
Because we've got f of 3 equals 2.
Yeah, that tells me when x is 3, y is 2. So, and we know what our slope is right here. When x is 3, our slope is 5. That's what it tells us there. So we have 5 times 3 plus b. Now what? What'd you do now?
Well, we got 15 there, so we can just subtract that from 2.
So 2 equals 15 plus b. That gives us b equals negative 13. So our tangent line, the tangent line is y equals 5x minus 13. Now what?
Just need a value that when we plug it into x, will get us negative, will get us 13, so that it can cancel out the value equals 0. Because we're trying to find what the 0.
How do we find a 0?
Plug in y equals 0.
So let's make that 0. So I have 0 equals 5x minus 13.
Yeah.
And then?
13 equals 5x, so 13 over 5.
So x equals 13 over 5. Nice. Nice work. A little sloppy on my part, but let's try that again. 13.
So much better.
So it's not that intimidating, right? I mean, it's wordy, but don't let that trip you on the test. It's just a matter of understanding everything. That's part of the reason why I introduced this problem in there, because I thought it could trip students up. I don't want you to feel intimidated. So which one is the answer? A, B, C, D, or E? Louder? Let's see. Let's see. Right, I want to talk about another, I'm going to switch gears. I know I only have about 10 minutes left. I want to talk about what is called differentiables. I'm going to talk about what is called differentiables. How much room do I have down here? So zoom in. So this is a new main idea. So the first main idea is linearization, and the second main idea is differentiables. Now consider when we take the derivative of something. I have something like y equals 2x plus 5. When I take the derivative of this, dy dx, this equals what? What does that equal? It is, yeah, the derivative of 2x plus 5 is just 2. So what this means, this is the slope. And if you recall, slope is a rise over run. A rise over run. What we're looking at is the change of y over the change in x. Isn't that what slope is? Isn't slope rise over run, or the change in y over the change in x? So what does dx mean by itself? Or dy? Or d theta? What do these mean by this? These are called differentiables. What does this mean? What does this mean by itself? Yeah. All right, because you're thinking of the average rate of change. If you're thinking of the difference in y over the difference in x, isn't that the average rate of change? So just generally speaking, when we talk about slope, we're talking about the change in y over the change in x. So this piece here by itself means what? Yeah, that's the change in x. By itself, that just means the change in x. This means I'm going to use red. The change in x. What's this one? Yeah, the change in y. And this one? Yeah, it's the change in theta. The change in, I'll write it out, theta. So those are what is called differentiables. So I want to find, here's my example, find dy and evaluate dy for the given value of x and dx. I'm given y equals x cubed minus 3x, comma, x equals 2, comma, dx equals 0.05. What do I do? I want to solve for dy. How do I do it? Kata, how do I solve for dy? Can't we take the derivative of this? Okay. If I take the derivative, I get dy dx. So the derivative of y with respect to x, and that's going to equal what?
3x squared minus 3.
Okay. Is there a way I can solve for dy? How?
Well, we already know the difference in x. Can we not apply it to the value of x?
What's happening over here? How can I get dy by itself? Yeah, multiply both sides by dx. I'm multiplying it all. Dx divided by dx gives me dy equals 3x squared minus 3 times dx. I solved, it wants me to solve for, it says find dy, I did. Now I need to evaluate dy for these values here. The question is how? Exactly. We're going to plug in x and plug in dx. So I have dy equals 3x, which is 2, squared minus 3 all times 0.05. What'd you get? So dy equals 0.45. So when the change of x is 0.05, the change in y is 0.45. When the change of x is 0.05, the change in y is 0.45, yep.